in earlier sections, we've looked at graphing linear and quadratic functions and at their applications to business problems. In this section, we'll be looking at higher order polynomial functions and how to graph them. But what do I mean by a higher order function? If I have, let's say, y equals 3x minus 2, that is a first degree polynomial because the exponent for x, we don't write it, but the exponent would be 1, so first degree. If I have y equals 4x squared plus 7x minus 10, this is a second degree polynomial because of that highest exponent of 2. In this section, we're going to be looking at third and fourth degree polynomials, such as perhaps y equals 1.5 x to the fourth plus x cubed minus 4x squared minus 3x plus 4. For a polynomial like this, we don't have as many clearly defined procedures for graphing, but there are a couple of general procedures that will help us to graph. The first one is the rule about x-intercepts. Okay, we know that a linear function, if it crosses the x-axis, can only cross it one time. A quadratic function that crosses the x-axis will either touch it and turn around or cross it twice, no more than twice. And the rule for x-intercepts is that whatever the highest degree exponent is, or highest term, there will be no more x-intercepts than that. So since this is a fourth degree equation, it will have 4 x-intercepts or less. Okay? Might not have 4, but it won't have any more than 4. Okay? The other rule is about peaks and valleys. Okay? A linear function doesn't have peaks and valleys. It's a straight line. A quadratic function might look like this and have one peak. Okay? A third degree function frequently looks something like this. And I have one peak and one valley. So the rule for peaks and valleys for this one, since the degree is 4, is 3 or less. Okay, a fourth degree polynomial, the number of peaks and valleys will be 1 less than the degree. And again, this is a maximum. We might have fewer than that, but we won't have any more than that. Let's look at an example. Okay, we're going to start very simple with f of x equals x cubed. So this is a third degree polynomial, and it's what we call the parent of all third degree polynomials. It's the simplest one we can get. Okay, there's no coefficients, there's no terms other than the cube term, and so it's the parent function. Everything else we get by adding to this. So to graph this, I'm going to make a table of values, as I've done before, and start at -2 and go up to positive 2. So negative 2 cubed is going to give me negative 8, negative 1 cubed, negative 1, 0 cubed is 0, 1 cubed is 1, and 2 cubed is positive 8. So to graph this, I'm going to make these 2 each. And I'll make these just 1 each. So plotting my points, at negative 2, I'm at negative 8. Negative 1, I have negative 1. There's my origin. Positive 1, and positive 2, positive 8. I'm going to connect these with a smooth curve. And that function looks something like that. Pause your video now and work on checkpoint number 1. In this example, we'll be looking at graphing a 4th degree polynomial function. So here's our function. And we're going to do exactly the same thing we did before. Of course, we'll have some different values. Okay, so for this one, negative 2 to the 4th would be 16. Divided by 2 would give us 8 times 3, so 24 here. This would, negative 1 to the 4th is going to be 1, so this is just 3 over 2. 0, 3 over 2 again, and 24 again. So you can see, just like our 2nd degree polynomial, this polynomial is symmetric. So let's, since all our y values are positive, I'm going to leave the y pretty low, the x-axis pretty low. And we'll make the y-axis right in the middle again. And we need to go all the way up to 24. So I'm going to go by 4s. On this axis, I can use 1 unit per block. So plotting my points, I have negative 2, positive 24, negative 1, 3 over 2, right about there, 0, 0, and then the other side is symmetric. So I get this shape. It looks a little like a parabola. It's kind of flatter on the bottom, but generally it's the same kind of shape as a parabola. And I'm not saying that all 4th degree functions are going to look like this. Sometimes they have a little more interesting detail there near the vertex. But this is a general shape that we would have for a 4th degree polynomial. pause the video now and work on checkpoint 2. Before we work any more on graphing, I'd like to go over some general rules about the shape of polynomial functions. We saw that for y equals x cubed, even if we put a number out here, the shape generally started low, did something in the middle here, and ended high. And this is the general shape for a cubic polynomial. Now even if I had an a out here, this would be the general shape. But if I had, I'm going to use negative a to signify a negative coefficient here, something's going to happen to this polynomial. Instead of starting low and beginning high, it's going to start high and end low. So it'll look like that. In our example, we saw that a 4th degree polynomial looks something like a parabola, but a little bit flatter on the bottom. And if that a happened to be a negative number, that also would flip that graph over. Okay, and these are not absolutely all the shapes. There can be some variation. Okay, this 3rd degree graph could have much sharper turns, and they might not look real even. A 4th degree graph could look a little bit more like a W and have better defined peaks and valleys. And as the degrees go up, a 5th degree polynomial is going to be similar to a 3rd in that it starts low and ends high as long as a is positive. But it could have a little more interesting center. So I've got 1, 2, 3, 4 peaks and valleys. But it's always going to start in one corner and end in the opposite corner. Even degrees are going to start from one direction and go back to that same direction, whether it be from positive back to positive or from negative back to negative. These are even degrees. These and this are odd degree polynomials. So I'm going to have a function g of x equals x cubed minus 11x squared minus 32x plus 24. And we're not going to actually graph this, but I'm going to show you a picture. And I want you to tell me if this could be a complete graph of this function. Okay, I've got a point up here. I have an intercept about here and another intercept maybe here. And I'm asking you, could this possibly be a complete graph of this function? When I say complete graph, I know that the function is going to eventually go on and on forever and be pretty much straight part. But for a complete graph, I want to make sure that I've got all of these turning points included and all of the solutions or x-intercepts included as well. So for this third degree polynomial, could this be the graph? And the answer is no. Because I've got just one peak, and it's possible that that could still be a third degree, but I would expect to see two. I would expect to see 3 x-intercepts, and I've only got 2 of those. Okay, but how do I know for sure that this is not a complete graph? I know for sure that it's not because a third degree graph is either got to start low and end high, or start high and end low. Well, this, in this picture at least, looks like it starts low, but also ends low. So either it's got to come up over here or it's got to come up over here to be a complete graph. Since the coefficient of x cubed is 1, positive, I would expect to use this shape. So I think there's got to be another x-intercept somewhere over here. So this is not a complete graph. Okay, how would I get a complete graph of this? There's a number of ways I could do it. If I know what this x-intercept is and this x-intercept, I can use those to reduce the degree of this function to something that's a little easier to graph. But for right now, I'm satisfied to know that this is not a complete graph, and I need to keep working on it if I need a complete graph. Okay, let's go on to another function. This one's in a little different format. It's already been factored for us. So what do I know about this function? By my zero product property, I know that it's going to have x-intercepts at values of x that make each of these 0. So the x-intercepts, or solutions is another word we can use for that. For this factor, if x equals -2, the whole function is going to be 0. So -2 is an x-intercept. This factor is going to give us +1 for an x-intercept. And this factor, you might have to do a little scratch paper math here and say 2x equals +3, and x is 3/2. So that's another solution or x-intercept. So let's plot these. Okay, I've got one at -2. And these are all pretty small numbers, so I'll just use 1 unit per block. So I've got an x-intercept there. My next one is at +1. And then I've got one at 3/2. So those two pretty close together. Okay. How did I know that this was a third degree polynomial? If you don't know that, go ahead and work on checkpoint 3. If you do understand why this is a third degree polynomial, you can skip that checkpoint. So in this third degree polynomial, I've got my 3 x-intercepts. My leading coefficient is a positive number, so I know I'm going to come up from here. And somewhere up here, I'm going to have to turn around and go back here, and then turn around and go back through this one. So that's the general shape of my graph. If I want to be more precise, I could find the y-intercept to give me another point. I could pick x to be -1 and see what that did for me. And I can plot really as many points as I would like to kind of smooth out my graph and make it a little more accurate. But a lot of times this is all we really need to see. So pause the video now and work on checkpoint 4. There are some additional examples in the textbook using graphing calculator, but we will not be covering those, and I will not ask you to do anything that you cannot do without a graphing calculator. So when you're finished with that last checkpoint, you'll be ready to work on your homework.